So we're going to be looking now at another type of argument, a very common type of argument. Arguments where you generalise from a sample. So you have a sample of cases, and then you use that as evidence to generalise from to what's true of the whole population of interest. Just so you come across it, sometimes people use the word inductive to refer just to arguments of this kind. Arguments where you generalise from a sample. I'm using inductive much more broadly to mean any argument that makes it's not deductively valid but makes the conclusion more likely. But you might come across the term induction for this special case too. They are, in my sense, inductively valid arguments, not deductively valid ones. Find them in lots and lots of fields. Some useful terminology for discussing them is this: sample, population and target property. So the sample are the cases you actually looked at. The population is the group you want to generalise to. So you don't want to just say what's true about the sample. You want to use that sample to make a generalisation about some wider class from which that sample is drawn. We call that the population. The target property is the thing that you're measuring, the thing that you're interested in, the feature of interest. So, start with some examples. Here's a quality control example. So you take a random sample of iPads off the production line, random sample of 50, and you found that 10 of them were faulty. That's 20%, right? So you make a generalisation. 20% of the iPads made at this factory are faulty. The sample is the 50 iPads you looked at. The target property is whether they're faulty or not. The population is not all iPads, but all iPads at this factory. Right? That's what you're generalising about. That's what's mentioned in the conclusion. So probably 20% of the iPads made at this factory are faulty. So they're generalising to a population of iPads just at that factory. Here's an opinion poll example. A Gallup poll conducted in 2006 said that only 33% of Americans approve of the president's overall job performance. The poll was based on telephone interviews with 1,000 adults. I really need to update that now, because it'd be interesting to know what the figure is now for the current president. The sample is the 1,000 adults that were actually interviewed, people you actually talked to. That doesn't include the people that you rang up and who said, "Oh no, sorry, I'm too busy," and hung up. Right? It's the 1,000 people you actually talked to. The population is all adult Americans. Right? Here it just says Americans, 33% of Americans, right? But they're probably not meaning to include infants and children. So I said the population is adult Americans in that year. The target property is whether a person approves of the president's job performance or not. Here's one from physics. Nearly all the factual information that physicists have about things comes from generalising from samples, right? So scientists have measured the half-life of radioactive elements like carbon-14. Half-life means how long it takes to become half as radioactive as it was. And they found the half-life of carbon-14 is 5,500 years. Right? Because I haven't tested every possible bit of carbon-14 everywhere in the universe. They've just tested the sample, the bits that we have access to right here on Earth. Right? So this is their generalising from a sample. Sample is the carbon-14 examined in experiments. Population really now is all the carbon-14 in the entire universe. Probably also past and future, because physicists tend to believe that things like half-life don't change the intrinsic properties of the substance. target property here is half-life. And here's just an everyday example. I don't like circuses, so I won't go with you to Cirque du Soleil. Every circus I've been to, I've hated it. So this person is generalising from a sample. The sample of circuses they've been to and experienced, and they're generalising that to all circuses. The target property is, whether I'm going to enjoy it or not, something like that. Being hated or not by me. Getting the idea? So here's one for you to try. A 1989 study reported that 65% of students in Ontario universities are moderate drinkers. Clean living Canadians. The Addiction Research Foundation undertook the study. From 4 unidentified Ontario universities, 13,200 full-time undergraduates were randomly selected. Questionnaires were distributed by mail. 5,000 students responded. What's the sample? %91% of you are saying B. 5,000 full-time undergraduates. There's a few for each of the other options. A and C also people are going for. B's the right answer. The sample is those 5,000 students. Not the 13,000 who were contacted, right? Those are like the people in the opinion poll who hung up the phone and said, no, I'm not taking part. We don't know anything about the people who didn't return the questionnaire. Only 5,000 returned the questionnaire, so that's the sample. They were taken from 4 Ontario universities, so C is close, but it's the students in the sample that we're interested in. Mainly. Okay, so what's the target property? A, how much Ontario students drink, which is the right answer. Right? That's what they're trying to determine. That's the feature of interest that they're trying to measure. How much Ontario students drink. What's the population? This is often the hardest question because sometimes the population isn't entirely clear. What do you think it is in this example? What's the population they're trying to generalise to? Here's the one I chose, D. I chose that because that's what the conclusion of the argument says. It's what they actually tried to generalise to. The study reported that 65% of students in Ontario universities, so all Ontario university students, not just the 4 that the sample came from. That's the population they're trying to generalise to. Now you might say, but actually they've got no right to generalise to all university students in Ontario, because there might be something special about the 4 universities they chose. So perhaps they can only really, they should only have tried to generalise to that. In fact, they tried to make a broader generalisation, which is why I chose D. So these arguments, inferences from a sample, I shouldn't say inductive here because I'm using that. It's a more general term. But anyway, these inferences from a sample all look like this. Certain proportion or percentage of cases in the sample had the target property. Conclusion, perhaps with some margin of error, that same percentage or proportion is true of the whole population. That same proportion of individuals in the population also have that property. Some arguments like this are good arguments, some arguments are bad arguments. It depends on the sample. and how representative it is. So I'm going to talk now, I'm going to approach this topic of representativeness by talking about some of the ways samples can fail to be representative. I will in passing talk about some of the ways they can be representative. One problem is sample size. Right? You kind of know this already, right? Generally speaking, the bigger the sample, the more reliable it's going to be, the more representative it's going to be. A different problem, though, is bias. Sample might be very, very large, but still biased for various reasons. Biased here means not representative of the population. Another problem of a different kind is how did you measure the target property? That can be done in more or less reliable ways. So let's talk about sample size first. Obviously, it's amazing really how everyone knows that a sample of 1 is not big enough. Nonetheless, arguments like this are extremely common. My grandfather smoked all his life and never had a day's illness, so cigarettes can't be bad for you. Right? Well, what's the sample there? It's the one grandfather, and we're trying to make a generalisation from that. Don't marry him, he's a brain surgeon. I met a brain surgeon once and he was a total asshole, right? Again, you're generalising from a sample of 1 brain surgeon that you met. Obviously not big enough. Nonetheless, quite common arguments. I said everyone knows in principle that, you know, the bigger the sample, the better, generally speaking. But why is that? I want to talk a bit about that. I want to talk about this principle I call the sample size principle. It applies particularly to random samples. Technically, the definition of a random sample is this. It means every individual in the population had an equal chance of getting into the sample. It's not that some individuals in the sample were more likely to be sampled than others. Everyone had an equal chance of getting into the sample. Right? When you have a random sample, those tend to be very representative, and the bigger the sample, the better. Why? Because when you have a smaller sample, you're more likely to get atypical results than when you have a bigger sample. Bigger the sample, the less often you get atypical results from sampling. So, to illustrate that, suppose I did this. I've got an ordinary pack of cards, and I do 2 different processes. So in the first process, I shuffle the pack, and then deal out 4. Right? Now, in the pack, there are equal numbers of red and black cards. Right? When I deal out 4, am I going to always get equal numbers of red and black? No. Right? Sometimes I'm just going to get 1 red one, sometimes I'm going to get 2, sometimes 3, sometimes 4 red ones. Right? 2 red ones and 2 black ones is, if you like, a typical result. That's what's representative of the true proportion in the population. Compare that, suppose I just kept doing that. So I shuffle the cards, deal out 4, count how many reds I get. Then I do it again, collect them back up, shuffle the cards, deal out 4, count how many red ones I get. I'm going to get pretty much a different number of reds each time. Sometimes it'll be 50-50 and sometimes not. Now compare that to doing exactly the same thing but with a larger sample size, 8 cards this time. So now I deal out 8 and count how many reds I've got. Again, the typical result, if you like, is 4. That's the representative result, half. 4 red and 4 black, but I'm not going to get that every time. Sometimes I'm going to get just 1, sometimes I'm going to get 2. So, ask yourself this question. Would you get imagine this extreme result of getting all red cards in your sample. Would you get that more often using process A or process B? A is the right answer, right? You're going to get the atypical result more often with the smaller sample size. You're going to get, it's much more likely you could get 4 red cards than 8 red cards, given that there are 50-50 in the pack. So obviously I have nothing better to do with my time than do this experiment 100 times at home. So I actually did it, and here are the results. So at the back in purple, you can see the results from dealing out 4. This is the sample of 4. So the most common thing was 50%, 2 red and 2 black. But I also got quite a lot. So what's that? 1 red card. And sometimes I got no red cards. That's about 9% of the time. Sometimes I got all red cards. And very often I got 3 red cards. It's still kind of peaking around the true proportion. But now look at the sample of 8. I get the extreme results much less often. I never got no red cards, and I only once or twice got all red cards. I've got these results, but again it's peaking around the average. Right. So with the smaller sample, the one at the back, you get the atypical results more often than with the larger sample, the smaller sample. So the smaller the sample is, the more likely you are to get atypical results. Larger sample, atypical results. By atypical I mean not representative of the proportion in the population. You're going to get those less often with the larger sample.